Hey chemists, today we're going to learn about electrochemistry. Electrochemistry is the branch of chemistry that examines the chemical changes produced by electricity, which are moving electrons, a current of moving electrons, and the production of electricity through chemical reactions. It's the study of chemical processes that cause electrons to move. What we can do is we can transform the chemical potential energy into energy used to do work by lowering the potential energy of electrons. So we're really going to be interested in looking at a specific type of chemical reaction that we discussed in the fall called redox reactions. Redox reactions stand for reduction and oxidation reactions. These together will produce a flow of electrons that could be used to power electronic devices, like a battery. In a later lecture, we'll discuss how batteries work. For now, we will talk about redox reactions. Redox reactions are oxidation and reduction reactions together, and we gave you a mnemonic in the fall to help keep track of which one is a loss of electrons and which is a gain. Leo the lion says grr. This stands for loss of electrons results in an oxidation half reaction, whereas a gain of electrons results in a reduction half reaction. Due to the law of conservation of matter and energy, we already know that matter cannot be created nor destroyed, and it's the same for electrons. Electrons can't be created, and they can't be destroyed. So any electrons that are lost in a chemical reaction must be gained by some other chemical species in solution. In an oxidation half reaction, the electrons are lost, so atoms become more positive. In a reduction half reaction, the electrons are gained, so atoms are becoming more and more negative. Sometimes it's helpful to picture a number line. If we have a number line where this is 0, and we have a positive 1, 2, 3, 4, 5, etc. on this end, and a negative 1, 2, negative 3, negative 4, etc., whereas in this direction, we're becoming more positive, and in this direction, we're becoming more negative, we can see what an oxidation half reaction looks like. In an oxidation half reaction, electrons are lost, and as an atom loses electrons, it's becoming more positive. In a reduction reaction, so let's go ahead and write this on here. This is an oxidation half reaction where there's a loss of electrons to become more positive. In a reduction half reaction, there is a gain of electrons, and if you gain electrons, you become more negative. So we're going in this direction on our number line. One of the things we're going to talk about today is an idea of oxidation numbers. Oxidation numbers are numbers that are found on the periodic table. So if you don't currently have your periodic table out, please go ahead and take it out and look at it with me. Right above the elemental symbol on your periodic table are a set of numbers. For some elements, there's only one number, and for some, there are more than one. These represent the oxidation number of the element. An oxidation number is the number of electrons that an atom will either gain or lose to fulfill the octet rule. And this is typically what we see. We use this term happy atoms. Obviously, atoms are not a living thing, so they're not really happy or sad. But what we really mean by this is stable atoms. This is the number of electrons that an atom will lose or gain to ultimately lower its potential energy. There are, of course, exceptions. Two of the exceptions that we encounter quite a bit are that of hydrogen and helium. Hydrogen and helium are stable with only 2 valence electrons. And of course, the octet rule means that most atoms are stable with 8 valence electrons. go ahead and take a look at some rules for how we assign oxidation numbers for an atom or for an element. Number one, all elements are going to have an oxidation state of 0. For example, if I were to give you elemental aluminum and ask you to figure out its oxidation number would be 0. The reason being, the total number of electrons equals the total number of protons for a neutral element. Rule number 2 says a single atom ion has an oxidation state equal to its charge. For example, if we have an ion of manganese with a +2 charge, we know that the oxidation state of manganese is also +2. Rule number 3 talks about polyatomic ions. Remember that polyatomic ions are groups of atoms that are covalently bonded together, and collectively they share a charge. So if we were looking at a polyatomic ion like nitrate with a -1 charge, the oxidation state of the entire polyatomic ion could be determined by figuring out the sum of the oxidation states from each individual atom within the polyatomic ion. So let's go ahead and take a moment and determine what the oxidation states for each of the different elements would be on the nitrate ion. One of the things I like to do here is separate out the atoms and take a look at the individual charges of the atoms and multiply them by the number of atoms that we have and set it equal to the total overall charge. So we've got 1 atom of nitrogen. So we're going to do 1 atom of nitrogen times the charge or oxidation state of nitrogen plus 1, in this case we have 3 atoms of oxygen times the oxidation state or charge of oxygen. And this is all going to be set equal to -1 here. So what we want to do is we want to figure out first the oxidation state of the atom that we are most certain about. So in this case, oxygen is what we want to look at first. Oxygen almost always has an oxidation state of -2. There is one exception that we will get to here in rule number 5. Oxygen is only going to have an oxidation state of -1 when it is with a peroxide. In this case, this is not a peroxide, and so oxygen would have a -2 charge here. If oxygen has a -2 charge and there are 3 atoms, then 3 times -2 gives us a charge of -6. So we really need to figure out what plus a -6 gets us to a -1. And of course, the answer is +5. In order to check and make sure that we've done this correctly, please look at the periodic table, find nitrogen, which is atomic number 7, and we want to look above the symbol for nitrogen and see if an oxidation state of +5 is even an option. And we see that yes, in fact, nitrogen does sometimes have an oxidation state of +5, so we did it correctly. There is a difference between oxidation number and charge. Sometimes we use those terms interchangeably, and we need to be a little bit careful about that. Charge is a physical property that can actually be measured. We can measure the number of protons and we can measure the number of electrons and determine the difference and therefore the charge. An oxidation number really isn't a true thing. It's really just a tool for us to be able to track electrons and the movement of electrons from one species to another. Let's go ahead and take a look at the rule number 4, which is net charge on a molecule. Looks like anytime you have the net charge on a molecule, it is going to be equal to 0. So if we had water, for an example, because there is no charge up here, there's no positive or negative sign, that means that the overall charge is 0. It is a neutral molecule. Rule number 5 talks about oxygen. So again, almost always, oxygen is a -2 oxidation state. The only exception to that is if peroxide is involved. If there's peroxide, it's going to have a charge of -1. Remember from the fall that peroxide is a polyatomic ion where two atoms of oxygen are covalently bonded together, and overall the peroxide ion has a -2 charge. So some examples of what this would look like is any alkali metal bonded to oxygen in a 2:2 ratio means that peroxide is involved. So some examples here would be H2O2. This is in group 1, even though hydrogen's truly not a metal, but this is hydrogen peroxide, where it is in a 2:2 ratio. We know the oxidation state of hydrogen is typically +1, and therefore, if I have 2 +1 charges, oxygen's charge must be -1 in order to balance out and have a net charge of 0 on the molecule. Another example of that would be lithium peroxide or sodium peroxide, or again, any alkali metal combined with oxygen in a 2:2 ratio. Last rule here, number 6. Hydrogen usually has a charge of +1. The exception to this is if it is a hydride, which has a charge of -1. Typically, we see a hydride combined with any kind of metal, cation. So an example of this would be calcium hydride, where calcium is a metal. We know metals typically have a large atomic radius compared to nonmetals with loosely held electrons. So calcium is going to give up electrons, and in this case, hydrogen being bonded to it is going to act as a hydride and therefore accept electrons from calcium. So in this example, calcium has a charge of +2, and hydrogen would have a charge of -1. And there are 2 of those, so we would actually end up with an overall charge of 0. So calcium plus hydrogen, 2 times its oxidation state equals 0. We know calcium only has one oxidation state, which is that of +2 if we look at the periodic table. So we know this is +2, and we know 2 times this has to equal the net charge of 0. So this must be a -1 charge, which is a hydride. All right, let's go ahead and take a look at some practice problems here for our oxidation numbers. Our first problem is Br2. So we have the diatomic bromine. And when we look at this, we see that bromine is going to have an oxidation state of 0, like any elements that are neutral on the periodic table. For number 2, we have aluminum fluoride. In determining its oxidation states, the first thing we want to do is look to see if either of these atoms has only one oxidation state available. And when you look at aluminum, the only possible oxidation state for aluminum is +3. Now, if we take a look at fluorine, the only possible oxidation state for fluorine is -1. And that makes logical sense when we think about where fluorine's position is on the periodic table. Fluorine is in group 7, which is our halogen group. And we know our halogens have only one more electron in order to reach a stable state of a full octet. So fluorine is also very small in terms of its atomic radius and extremely electronegative. It's the most electronegative atom on the periodic table. So we know fluorine is going to be very attracted to those electrons, and it will gain 1 electron to achieve a more stable state. If we go ahead and verify this using our method to track oxidation numbers, we have 1 atom of aluminum plus 3 atoms of fluorine, and the overall sum of the charges has to equal 0 for this neutral molecule. So we put our +3 in, our -1, and we get to 0. Number 3, I recognize right away that I have an alkali metal combined with oxygen in a 2:2 ratio. So I recognize this is peroxide, which is a special state for oxygen. Oxygen has a -1 charge, and sodium being an alkali metal, only has an oxidation state of +1. So sodium will always be +1. Number 4, we're getting a little bit harder with a polyatomic ion here. So the first thing that we want to do, since chromium has multiple oxidation states, is look at oxygen. First question we ask ourselves, is oxygen a peroxide here? The answer is no. Therefore, oxygen's oxidation state must be -2. So if we take a look at this and we see that we have 2 atoms of chromium plus 7 atoms of oxygen with a -2 oxidation state, the overall charge here has to equal that of the charge of the ion, which is -2. So I need to figure out what plus -14 gets me -2, and that would be a +12. 12 divided by 2 is a +6. I look at the periodic table, and it turns out that chromium does have an oxidation state of +6. Number 5 is pretty easy here. On number 5, we see that copper has a +2 charge, so we know its oxidation state for a single atom ion is also +2. Number 6 is ammonia. When we take a look at this one, we first want to look at the possible oxidation states for hydrogen. We know that hydrogen can either be a +1 or a -1. It is only a -1 hydride when it is combined with a metal. It is not, nitrogen is a non-metal, so we know hydrogen must have a +1 charge. If we take a look at this, if hydrogen's a +1 charge, we have a +3. In order to equal 0, nitrogen must be -3. This also makes logical sense, guys, when we think about it, because nitrogen is much more electronegative than hydrogen. So nitrogen is going to be likely to attract electrons, whereas hydrogen is more likely to give them up. This is the topic of your problem set 1202. So please take a few minutes and look at problem set 1202 and get some practice.